Hello, everyone. Welcome to this webinar on hydroturbine design and performance analysis using cloud-native simulation in SimScale. I am your host, Kanchan Garg, Product Manager for Rotating Machinery at SimScale. And joining me today to give you a live demo of the product is my colleague, Omar Ebed, who is an application engineer. And before we proceed any further, a quick reminder to all of you that your mics are going to remain in mute. Should you have any questions, please feel free to use our chat option. So let's start by quickly looking at the agenda for today's webinar. We will have a general overview of why we are here talking about hydroturbine simulations. Follow it up with what SimScale has to offer for generally turbomachinery analysis. And then Omar is going to do a live demo of a Francis turbine simulation setup in SimScale and discuss the results, post-processing, visualization, and what you can get out of a typical simulation in SimScale. And of course, at the end, we will open up the floor for question and answers. So as I said, let's start by looking at why we are here today talking about hydroturbine simulations in the first place. So as you can see from the pie chart here on the left, hydroelectricity accounts for about 15% of all electricity generated, and it is more than all the other renewables put together. And to achieve net zero scenario by 2030, it is imperative that this sector should grow at least 3% annual growth rate. Now, what that means is that old hydropower plants, which were, probably installed 30, 40 years ago, need to adapt to the changing situation, to the new regulations, new requirements, as well as the changing um, climate situation, which also puts a huge strain on the available water resources. And this has to go hand in hand with new capacity addition, which also has to operate optimally despite the huge variation in water resources. And as you can understand, obviously, hydro turbines are at the heart of any hydropower project. So it is imperative that turbine design needs to see a lot of engineering innovation to meet the overall goal of this industry. And that's why we are here talking about why or how simulation and SimScale can really contribute towards this goal. So as you know, turbines come in many different types, sizes, and what you can see here are three of the most common ones, depending on what head they generate. But also any type of turbine will mostly work far away from its best efficiency point. This is because of changes in the grid demand. It is because of changes in the flow that is available, maybe due to climate factors such as drought or in any kind of water regulation. And flow through turbines is obviously very complex. And now designers and engineers also have to factor in ecological impacts, like, is it harmful for aquatic animals? Are there any government instated water regulations to take care of? And obviously, any kind of hydropower plant is a huge investment that takes quite a bit of time for installing and starting operations. So any kind of suboptimal performance can really prove costly in the long run. And that's where simulation has a huge role to play. I'm sure all of you are already aware of the benefits of simulation, where you can estimate the performance of new designs or troubleshoot existing turbines without actually going into physical prototyping. And the physics or the numerical methods behind hydro turbines has been in place for about 30, 40 years now. So it's possible to really go deep into understanding the complex flow behavior that happens inside a turbine, while also taking into account all the ecological factors that I just mentioned. However, simulation traditionally has been limited to these very niche on-premise software, which in itself has its own investment and own technical and economical barrier involved. So you need experts in-house who understand those software, not only the hydroturbine field, but also how to use different modules. And then there is the hardware, upfront hardware that you need to invest in order to run these simulations. So that's where simulation in SimScale comes into play, where SimScale's motto is basically to break down this economical and technical barriers to simulation and make it truly accessible to every engineer at every stage of the design and design cycle. And how we are doing that? We are doing that by investing in really industry validated solvers and numerical methods that have been around for many years, and combining that with our proprietary cloud architecture to enable fast design prototyping without investing in any kind of multiple software licenses or in and zero, literally zero hardware investment. So basically we are at the forefront of early simulation and iterating on designs faster using simulation. And that's what I would just like to go a little bit into what is behind the technology of SimScale for Turbomachinery. On the CFD side, we have a proprietary CFD solver based on a binary tree measure and a finite volume based RANS method. It is specifically tailored for turbomachinery and valve operations. And because it is industry validated, we are confident of achieving about 2 to 5% accuracy of test data. And that's crucial here because fast on the cloud does not mean that there is any trade-off with accuracy, because obviously that's very crucial. And coming back to my point of not requiring many different tools or modules for doing different types of analysis, that's what SimScale is focused on, is to enable teams to actually focus on designing by giving them multi-physics analysis within the same platform. So along with CFD, you can also do structural and thermal analysis, for example, vibration and harmonic analysis of the runner, or how your support structure would respond to any kind of vibration, any kind of thermomechanical stress analysis. So basically what that means is that you can come into SimScale with your CAD, do a CFD analysis, follow it up with a structural stress analysis maybe, and how the thermal profile is going to look like around your components, and a vibration analysis. So all of this on the same platform. And we're also working very hard to make SimScale really integrable into your design process by leveraging our simple API, with which you can actually integrate simulation in SimScale with your other tools that you have in your stack. For example, if you have a preferred CAD tool, or if you have a preferred optimization or a PLM tool, it is totally possible to integrate SimScale seamlessly with all of them. Now, I'm going to hand over briefly to my colleague Omar, who is going to present a simulation setup and workflow for Francis Turbine. But I'd like to point out here that the steps that would be shown are not really specific only to Francis Turbine. The reason we have chosen this is because it's just one of the most popular type of turbines, but all of this applies to any type of hydro turbine. So without any further ado, I am now going to hand over control to Omar.
Thank you, Kanchan. Hello, everyone. So I'm Omar. I'm one of the application engineers with the SimScale team. So what I'm going to do here in a second is we're going to walk through the workflow of how you actually set up a simulation within SimScale. We'll start with just understanding what the requirements are of the geometry that you can bring in and how flexible that is, and then walk down the workflow of setting up a simulation to generate a characteristic curve for a Francis turbine. I'll also give some insight on just the post-processing side of things. So what mesh we develop in the end within the SimScale platform using our proprietary solver, as well as actually looking at the flow behavior and the results of several different operating conditions so we can generate our characteristic curve for the turbine. So just to give a quick rundown on the case that we're running here. Here I've defined the actual geometry. I'm presenting here the geometry as well as giving in context what the simulation setup will look like. So the operating range for this specific model of a Francis turbine operates between 5.4 and 9 cubic meters per second. So that is what we define as our flow rate coming in. For the outlet definition, at the end of the draft tube, we'll define a static gauge pressure, modeling essentially ambient conditions outside the turbine assembly. So in this case, a zero gauge pressure is in reference to the absolute pressure of the outside environment. Next, we of course want to define the rotational speed of the turbine. So in this case, we've defined a moving reference frame zone. You can see on the cylinder on the right-hand side here. This rotating zone allows you to model the rotation of the turbine, a runner. So we're bounding the runner faces in the flow domain by the cylinder. So we're going to model three different operating speeds, so 480, 600, and 720 RPM. Of course, we just define the gravity to be in the downward direction in relation to the actual assembly model. And for the fluid material, since this is a water turbine, we've just defined the density and kinematic viscosity of clear water. Now for cavitation modeling, that reference or absolute pressure is important. So for us to understand when cavitation is occurring within the flow domain, we'll want to define the absolute pressure, which is corresponding to where we're defining that zero gauge pressure, as well as the saturation pressure and the fluid temperature to actually model the cavitation based on the fluid properties of water in this case. So here's just a quick overview of the mesh that we can generate within SimScale. I'm going to go back to this in a second, but we'll kind of give you an overview of how automated this workflow is to generate body-fitted Cartesian mesh, which is what the solver is based on. So I'll go ahead and switch over to the SimScale platform. So as you can see here, I'm simply just working on simscale.com. So the essence of being cloud native is that you can work on any device, any kind of laptop or workbench, as long as you have an internet connection and have a login. You can go ahead and go on simscale.com and dive into one of your projects. So that's the essence of being cloud native and web browser native. So here we have the workbench of one of our simulation projects. In this case, this is the Francis water turbine simulation setup that we have here. On the left-hand side is where we'll be doing most of the work. This is where we can find all the different simulation setup settings that we can actually input, our own settings based on the case that we're running, as well as actually importing our geometry or creating new cases. So our first step is going to be to import our geometry. Now, we support all kinds of CAD file types, as well as the generic 3D model types. So we have Parasolid, IGES, and step file support, but we also work with CAD native files like SolidWorks, Inventor, Rhino, CATIA, Creo, NX, and there's much more down the line as well. So when you bring your model in, you can actually bring in your own, the original assembly of your turbine in this case. But if you already created the flow domain elsewhere, you can bring that in directly. Now, since this is a CFD simulation, of course, we want to be simulating the flow in the negative space where that water flow domain actually encompasses. So in this case, we actually want to make sure we create that flow domain. Now we can create that externally in a CAD program, or we can create it in our CAD mode if you have that solid body assembly. And it's really just a simple 3-click operation to generate that flow domain. The other requirement here is you'll notice again the cylinder, which is the MRF zone. You can see highlighted here. If I go ahead and make this model a little translucent, we can see that it's bounding the runner of the actual turbine. So we have our guide vanes externally around the rotating zone, which are not rotating. Those are stator guide vanes. And then we have our runner, which is rotating at a designated RPM that we define. So we want to make sure that the rotating body, the rotating cylinder zone defines the region that can rotate. Now, when we have our model brought in, we can go ahead and create a new simulation. So, as Kanchan had mentioned, SimScale is an inherently multi-physics platform, multi-physics simulation platform. So we can work with any kind of simulation type or analysis type, whether it's a CFD simulation working with heat transfer or multi-phase, as well as just structural analysis where we can model thermal loads, static load, mechanical loads, or dynamic loads and frequency analysis. In this case, I'll go ahead and set up a CFD simulation. In this case, this is using our proprietary rotating machinery solver. So that's called subsonic in this case. So I'll go ahead and create that simulation here. So you'll see that when I create a new simulation tree item shows up on the left-hand side here, which is where we'll be focused on. Now, if I want to name this simulation tree item something meaningful that I'll remember what this analysis specifically was about, I can go ahead and name that as well and save it. Now, before I go down the list here, what these red circles and green check marks are essentially saying is it's telling us as the user what parts of the simulation have been defined for us already and what parts still need our input to define the problem or the case that we're running. But over here at the top, we can see some of the global settings that we have here. So we're of course assuming that there's going to be turbulence, so we use our K-epsilon turbulence model. For cavitation, now this is an optional input, but we want to make sure that if we do care about modeling the cavitation in a rotating machinery application or valve flow, we want to ensure that we use our cavitation model. So we'll be modeling the gas mass fraction or the volume fraction in different regions of the flow domain. And in this case, we'll go ahead and simulate a steady state simulation, but we can also, of course, also set up a transient time-dependent simulation. So going down the list here, our model is already defined, which is really just the gravity modeling, but we'll want to ensure that we actually define it in the right direction. So in this case, we can see on the bottom right-hand side here, we have the navigation cube. So assuming negative z is down, we'll want to define that gravity magnitude and direction here. Next, we want to define our flow material. So in this case, we already have water as one of the default materials with the cavitation properties already defined for us. Now, the most important inputs in terms of just for any kind of use case, regardless of what the actual flow material is, for example, vapor molecular weight, liquid bulk modulus, and saturation pressure, those are all going to be dependent on just the flow properties of that specific flow material, in this case, water. Now, the ones that are more relevant to just understanding how it works in the simulation space in general is going to be the liquid reference pressure, and the liquid temperature is just defining the overall fluid temperature, because in this case, we're not modeling temperature changes, we're just modeling overall bulk flow temperature. But for the reference pressure, this is where we're defining the absolute pressure, which is what corresponds to zero gauge pressure. Going down the list here, we want to define our boundary conditions. So this is going to be our flow rate coming in and our reference pressure on the outlet. So here we can define one single flow rate. If we're just interested in looking at one operating condition, so we could just define that minimum for 5.4 meters cubed per second. Or I can parameterize this input by going to the table here and actually inputting all of those values. Now, I can actually go ahead and import a CSV file as well, if I would like to. If I already have that inputted separately, I can go ahead and do that. In this case, I'll just go ahead and input a subset of the operating conditions I want to simulate. So this is the 5.4 to 9 cubic meters per second flow rate coming in. Now, we would just want to simply define the face where that flow is coming in from. And then we'll do the same thing for the reference pressure on the outlet, reference gauge pressure, excuse me. So in this case, we'll just go with 0. Now the third, really most important step is going to be defining our rotating zone. So over here, we have the, we can define our rotating zones like origin and the rotational velocity. So first I'll want to actually select the body that's rotating. So this is our tool body that tells us where in the flow domain it's rotating at a specific speed. In this case, we can go ahead and look at which way the blades will be rotating. In this case, it'll be in the positive z-axis, so this is already correctly defined. And then we'll go ahead and work with these middle RPM, so that's around 62.3 radians per second, or about 600 RPM. Now, just a quick note here. In this case, I already know that it's mostly centered, but if my origin is elsewhere and I don't want to look at where that center of rotation is on the CAD, I can actually just go ahead and select the center of the tool body by just clicking on this button here. Now, from here, we've essentially fully defined our simulation, but there are some important additional steps for us to extract the plots and results that we are most interested in. So in this case, if we want to understand the power generated from the turbine, as well as the total pressure difference to determine the fluid power and determine the efficiency as well, we want to define some certain controls. Now, the forces and moments result control allows us to extract the power. In this case, I can just go ahead and select all the turbine runner blade surfaces. And then for the extracting the total pressure difference from the inlet to outlet to determine the fluid power that was extracted, that can be extracted. So using that as our efficiency factor. We can go ahead and define the inlet and outlet faces here, and then just ensure we're selecting total pressure. For the mesh settings, there's a very automated workflow that we can work from here. In this case, I can just go ahead and set a fineness level and let the let the mesher essentially automate the refinements near certain edges so that I don't have to do the workload myself. But we can also apply refinements, local refinements based on a certain tool body. So for example, I can define a cylinder on the correct axis here. And I could go ahead and actually refine a region within my flow domain and give it a maximum cell size in that region. So let's say we wanted to do 2 centimeters in this section near the guide vanes and runner. You know, go ahead and do that. Now, if I go ahead and kick off a simulation, since we've defined several different flow rates, we'll be actually kicking off an experiment. So we'll run multiple simulations in parallel, and we'll get an estimation of how long that will take. Now, since we're working based off the cloud, each of these simulations get their own instance. So we're running all of these simulations in parallel over here, as we can see. We're not waiting for one to finish before the next one to start, which is the beauty of running it in the cloud. Now going back here, we want to just quickly review the mesh that we've generated. So this is using the settings that I've shown, a fineness level of 3 in this case, from the simulation results that I'm about to present here, as well as 2 centimeters maximum cell size in this refinement zone shown here that you can see. So you'll see that it adapts near the leading and trailing edges of the guide vane and runner blades automatically with little workload from me. And we've developed a mesh size of 2.3 million cells across the flow domain without trying to so we can see that we're not trying to concentrate mesh cell elements in the bulk flow regions where we're not expecting complex flow behavior, but of course we've refined it as well near the guide vanes and the runner itself, where we're expecting a lot more turbulence in the region. So from these results, we can we can actually, since we were able to kick off these simulations in parallel, I can go ahead and kick off those 3 different RPM conditions simply by kicking off the first one, going ahead and refining that in the simulation setup and kicking off another set of flow rates. So in this case, I've run the 3 different flow rates: 480 RPM, 600 RPM, and 720 RPM. So from here, we've developed a characteristic curve for all 3 operating conditions, all 3 operating speeds. In this case, we've taken the power output from our result control and compared that to the fluid power that can be extracted in total from the turbine flow. Now, some things that we can also look at in the post processor really quickly is that we can investigate all kinds of flow behavior, but one thing that's quite difficult with a lot of solvers is actually modeling cavitation directly. So here we're looking at the total gas volume fraction of the flow near the runners, as well as down the shaft tube after or downstream from the runner. So what we can extract here is actually looking at the leading edge cavitation and modeling that directly, as well as seeing the extent of the draft tube swirl to see how we can further look at that design in a fairly rapid way, actually. Now, from here, I guess if you're interested in working with SimScale, reach out and we'll be more than happy to get you guys onboarded to see how SimScale can help you in any kind of simulation or a hydro turbine simulation especially. And with that, I'll leave some time at the end here for questions in general from the audience.
Thank you, Mar. So we do have a question coming in. Is there a way to parameterize the RPM and not just the flow rates?
Yeah, that's a good question. Absolutely.
Do you want to take that, Mar?
So yeah, I can go ahead and just kind of walk through. So in general, from the simulation setup, we can only parameterize one thing at a time. So if I'm trying to look at several different RPMs at a given flow rate, I can simulate that, or I can look at several different flow rates at a given RPM, as I've done. I can actually just quickly go back to the platform here. The one thing that's really nice about these parallelized simulations, though, is that since this experiment is running, so we have the 5.4 to 9 cubic meter flow rate experiment running at the 600 RPM condition, and I can actually go ahead and just name that as well to signify that this is 600 RPM in the case that I've just run. I could go ahead and go back up here and define it on the 720 RPM. So I think that's around 770 radians per second, and kick off another operating condition. So now I'm looking at generating a second curve for a second operating speed. And these are all running, each of these cases are running at the same time. We're not waiting for one to complete for the next one to start in any way. And so there's really no limitation on how many simulations you can run here or how many different operating conditions you can run. In this case, just to give you some context here. I just want to give some context here.
Sorry.
Looking at the 3 operating conditions that I've already run here, they take about 20 minutes for the most part. Looking at 3 different RPMs at the whole set of flow rates, which 10 different flow rates between 5.4 and 9 cubic meters per second.
Thanks, Amar. We do have a follow-up question that might need you to stay in the platform, and that is if you can show how you identify the rotating geometry again.
Oh, absolutely. So the rotate, so in this case, if I go ahead and hide the cylinder here, we're looking at a translucent view of the geometry. So we can see that there's the runner in the center over here. And we can actually highlight the selection here. So in this case, the runner, all the surfaces that are relevant for extracting that power output or power generated, we can select all these surfaces individually our first run through and then group them up in an entity set shown up here, so that we can go ahead and select that for our result control. Does that answer the question?
Well, I think so. And um, there is another question on, can you comment on the multi-phase capabilities? And I'll take that. So we already do have a multi-phase solver, uh, which is based on the OpenFOAM stack of tools. But now within our proprietary CFD tool, we are integrating a much more faster and robust solver, which is also based on the same numerical methods that I just talked about. And this should be available by January of 2023. And that would be the ideal the ideal tool for simulating any kind of impulse turbines, like free surface flows over turbines and anything else in between. I hope that answers the question. And one last question before we wrap up: what control do we have over other differences schemes used? And what about convergence solver? And also, what are the turbulence models? So I'll just start with turbulence models. The implemented model is K epsilon with specific coefficients and wall functions tailored for turbomachinery analysis. Within our subsonic solver, we do not have any other turbulence models available. And this is also because this is an industry validated tool which has been around for about 10-15 years. This is an integration that we do with a development partner. And this does really well already for flow control and turbomachinery aspects. In future, there might be an avenue to add more turbulence models, but that is not something we are focusing on in the short term. And in terms of the convergence method, it is a simpler based algorithm, pressure velocity scheme. I am afraid we are already 2 minutes over time. And whatever questions we could not get to, please continue. Just type in your questions and we will make a note of it and we'll make sure that we get back to you personally. Thank you all for joining us today. It was a real pleasure and I hope it was informative for you also. Thanks, Omar, for joining me.
Thank you, Kanchan, and thank you everyone for joining us today.